Now let's talk about Ampere's law. Ampere's law says that when you have a current generating B field, and then if you choose a closed loop and do the path integral of B dot ds along that closed loop, the integration value is going to be equal to a constant mu0 multiply the amount of current penetrating the surface that bounded by your closed loop. So in order to make this easy for calculation, we typically would like to choose the loop so that the loop is either parallel to the B field, so that B dot ds becomes simply the B value multiplied ds. Or we would like to, in some situation, we would like to choose the ds to be perpendicular from the B field. So for that part, B is perpendicular to ds at the B dot ds equal to 0. Also, to simplify this integral, we would like to choose the loop so that around the loop, the B field is equal everywhere. Then the B field is a constant for this integral so that B can be taken out of the integral, and this becomes simply the B field value multiply a total accumulated length for that loop. And then it becomes very easy to solve for the B field, and this method apply for certain situations when you have a very symmetric B field so that you can easily find those nice loop. Let's look at this B field. When we have a looping B field created like that, we noticed that one location is obviously different from any other location, which is the center of all those rings. Why? Because we noticed that if we are going to do a path integral of B dot ds, no matter which path we choose along those circles, we are always going to have some positive value for that integral. As long as we are including this part inside our path. However, if I'm going to choose a path not following the B field, if I'm going to choose a path like this, okay, and in this case, the B field and the ds, in some situation they are in the same direction, somewhat same direction, and in some other situations, for example here, the B field is pointing this way, and here the ds is opposite. In this case, when you do your B dot ds, you have some positive contribution and some negative contribution. After you finish this loop, you have total B dot ds entire loop equals to 0. Why is that? Because obviously by looking at this B field, you realize that it's a current B field source at this center, but not here. Also not anywhere here. Those regions, you have no current penetrating the surface bounded by those loop, so that integral becomes 0. Okay, and now let's look at the second right-hand rule. The second right-hand rule says that take out your right hand, align your thumb with the current, and then bend your four fingers. The direction of your four fingers bending is going to tell you the direction of the B field. The four fingers are going to bend along the B field direction. For example, in this case, we know we have a current going up, and we are creating B field into the page on this side and outer page on this side. So the B field is surrounding the current, forming loops. And the direction of those loops are indicated by my four fingers on my right hand. This way, okay, into the page, out of page. The reverse direction of current. Align your thumb with your current and you bend your four fingers. Then now you have B field into the page on this side and outer page on this side. Simply by flipping the direction of the current, you're going to make the B field changing from counterclockwise to clockwise, or clockwise to counterclockwise. Or even if you do not have a straight wire, you can still use this method. If you have a bended wire and a current like that, you can align your sum with your current, and then your four fingers can only bend this way. So on this side you have B field into the page, and on this side you have a B field out of page, and then here you have a B field like this. You have something into the page like that, and coming out the page on the other side, looping around the current. And then that's true for this part. That's also true for this part. That's also true for this part. So even if while it's bended, you always have into the page magnetic field this way, and then you have out of page magnetic field on the other side. Okay, now let's use the Ampere's law to find out the B field for some situation. First, if we have an infinite long while, when we say infinite, in reality, it may not be infinite. In reality, as long as it is very long, we can approximate and consider it to be infinite. And then we know that every point can be considered to be the center as long as it's long enough. And then surrounding the current, we are going to have a B field, looping and looping and looping. We have a small loop here. We have a bigger loop surrounding. Okay. Then, in order to figure out the B field at this particular location, P, which is at a distance R, P is at distance R away from the wire center. In order to use Ampere's law to find out the B field, we would like to choose the loop so that the B field is parallel to the loop. And also we want the B field to have a uniform value. Then we know, because the B field forms circles, we would like to have a circular loop instead of a rectangular loop. And we also want the loop to center exactly at the center of a wire so that every point on the loop is the same, the B field is the same. Also, it is helpful if we look at this from the top view. Okay, if you are watching from top, and then you're going to see the current coming toward you like that. That's your current coming toward you. And then the location P is here, which is at the distance R from the center of the wire. And then using our right hand, we know, align your thumb with your current. And then your four fingers are bending along the direction of the B field. So the B field is going to be form counterclockwise loop like that. That's your B field. Then we would like to choose integration path exactly following the same direction of the B field. So we have the integration of B dot ds for this loop equals to simply B multiply ds, because they are parallel everywhere. Take out a B, we are integrating the length of S, and that's easy. When we are integrating the entire circle, we always get B multiply the circumference of the circle, which is 2 pi r. That's the left side of this Ampere's law. What's the right side? The right side is easy, and that must be equal to mu0 multiply the total amount of current enclosed in this loop, or the current penetrating the surface bounded by the loop. In this case, it's just simply the amount of current I. That's it. Okay? If this is when you have one while, like here, if you have one while and you try to figure out the B field at this location, you can draw a loop and do exactly what we did, and we figure out that this location, the B field is like this. This is while A, and the B field due to A is equal to mu0 I over 2 pi r, and this is distance r, based on this calculation.